So, hello everybody, welcome to our weekly meeting. We're happy to have Ravid Ziv here, a PhD student from our department here at HUJI, supervised by Professor Tali Tishby. Ravid is a research scientist at Intel AI and was a research student at Google AI, worked with Dr. Alex Salemi, was awarded by Google to PhD fellowship in machine learning for 2018. Ravid explores learning and the dynamics via information theory and artificial and biological neural networks. Today, we'll talk about information flow in deep neural networks. So, Raviv, the stage is yours. Have fun.
Thank you, Elad. So today I'm going to talk about information in deep neural networks. So this is a joint work with my supervisor and Tali Tishby with Zoe Piran from the Hebrew University and Alex Salemi from Google. So let's start. So first of all, I will give some background. Then I will talk about information in deep neural networks and how can we look on information in deep neural networks. Then I'm going to talk about information in infinitely wide neural networks. And then if we have time, I'm going to talk about the dual information bottleneck. This is the information theoretical framework. Okay, so let's start. And if you have any questions, just ask. So I don't need to tell you that neural networks are working really good, right? Everywhere. But the problem is that we don't understand them. We need to understand them better. We don't understand them good enough. We don't know what is an optimal network. We don't have specific design principles, and we don't know how to interact their predictions and their representation. So in this talk, I will try to give a direction to how to answer some of these questions. So let's start with some short background. So some information theory background. So the KL divergence between two distributions is a measure how one distribution different from the other one. Okay, so this is this term, and the mutual information between two random variables x and y is the DKL between their joint distribution and the product of their marginals, and it's how many bits I know about x if I already know y. Okay. And now is the question, what is an optimal representation? So there are many answers to this question, but I want to present here some answer from information theoretic point of view. So we have our data, x, the observed data, and we have labels, y, and we want to create a representation. We want to use an encoder to encode our data to create a representation that will give us a good prediction about y. Okay, so this is the general framework, and the information bottleneck method tells something very simple. You want to find a good representation, so you need to compress x as much as possible, but at the same time, you need to capture the relevant information about y. Okay, so you have these two terms that you need to take into account. And now you can formalize it using this Lagrangian. So you have here two terms. So first of all, it's the information with your input. Okay, so remember, T is your representation, your model. So you want to compress your representation, your information with your input. from one hand, and you want to keep the relevant information about your labels, about what. And beta is a trade-off parameter that controls between compression and prediction ability. Okay, so this is the information bottleneck method from 1999. And so why to use this this method, or why to try to minimize this Lagrangian? So the information with the labels, the information with the labels is a performance measure. Okay, it bounds the prediction error. So here we have the expectation of log of if Q is our model. So log Q y given T is our prediction, or the log loss that everyone is using to optimize a network, for example. So here, so this expectation is exactly the log loss that we are interested in. So the information with the labels bounds it, bounds this performance measure. And why to use the information with the input? So you can think of it as an approximate minimal sufficient statistic. So in the general case, we don't have a non-trivial minimal sufficient statistic. So we can only approximate it. And it's also, we have a generalization gap that this information bounds the generalization gap. So the generalization gap is the difference between the train error and the test error. And we want that our model will generalize better, that this gap will be small as possible. And there are several bounds that actually tell you that if you compress, if you reduce the information with the input, then you will also compress, you will also reduce this gap, this generalization. Okay? So again, we have these two terms. Okay, so let's start with our first work, opening the black box of deep neural networks. And in this work, we suggested to look on neural networks from information theory perspective. So let's consider this simple feed-forward network. And we say that you can look on each one of the layers as a random variable. And now you can ask how we encode the input to this layer and how we decode our representation to the label. Okay, so again we have the encoder and the decoder, and you can look on the information that we have that each layer has on the input and on the label. Okay, good. And now we can look on what we call the information plane. So x-axis is the information with the input, and y-axis is the information with the labels. And the IB theorem tells us that we have some optimal bound that doesn't depend on a specific algorithm, that we cannot go above this bound. Okay, so we have our optimal bound. And now we can look on a specific network, we can measure the information for each layer in the network, and we can look how a specific network looks in this plane. So, for example, this is a network with five layers, and so this is the first layer in the network, and this is the output layer in the network. And we know from the data processing quality that the information along the network can only decrease. And now we can look how the different layers look like in the information, in this information plane and during the learning, for example. Questions? Good.
Yes. In the last slide, you made a separation between encoder and decoder. How do you decide which is which, or where do they transition?
So I'm taking a specific. I'm looking on the representation of a specific layer, okay, and I'm calculate the information with the input for this layer, and I'm calculating the information with the labels. Okay, I'm taking. You can think of it as an optimal decoder. This is the optimal base decoder. Okay. I'm not looking on the real decoder of the network. I'm looking what happens if I have an optimal decoder for each one of the layers. Is it answering your question?
I think that it answers enough so far.
Okay. Okay. And now we constructed a simple problem, okay? And we took a small network with 5 hidden layers and the activation function tangent hyperbolic, and we did here 50 different random initializations. Okay, so here each color is a different layer. So again, this is the output layer, and this is the first layer. And for each layer, we have 50 random 50 points for 50 random initializations, and we will look on it during the training process. So this is the information plan. X-axis is the information with the input, and Y-axis is the information with the label. And we look now. We will see a movie that describes the network, all the layers in the network during the training. So let's see. So we see that we have a first phase, a fitting phase, where all the layers increase their information with the labels. It's a fast phase. And then we have a compression phase that all the layers compress their representation. They compress their information with the input. Okay, so all the layers compress their information with the input and still increase their information with the labels till they have some optimal point. Okay, and now let's see it from a different perspective. So now what we have done here, again, it's the information plan. It's the same networks, same network and same problem. And now we averaged over the different random initializations. Now here the different colors are the different epochs. Okay, so this is the network at the beginning of the learning, and this is the network at the end of the learning. Okay, and for example, this is the path that the final layer is doing during the learning. Okay, and we can see here again that we start with some random initial state, and then we have a fast fitting phase that we increase, so all the layers increase their information with the labels, and then we see a slow compression phase till we have some optimal trade. Okay. Next. So we checked also the gradient. So this network trained with a stochastic gradient descent without any regularization. So you only have gradient in your network, the gradient of the stochastic gradient descent. So we measured these gradients, and we measure it by, so each epoch has many median batches. So we look on the mean for each epoch. We look on the mean of this epoch and the standard deviation of this epoch, and we can do it for each layer. So here, x-axis is the epoch, the numbers of the epochs, and each color is a different layer, and these lines are the means for each layer, and these lines, the dashed lines, are the standard deviation. And what we can see here that we have two distinctive phases. So we have a phase, the first phase is a phase with high signal to noise ratio, where the means are much higher than the standard deviation. And the second phase, when we have low signal to noise ratio, when the fluctuations are much higher than the mean. Okay, and this black line is the flipping point between the phase.
Can I ask a question?
Yes.
Just to make sure, the values here are the mean and the STD of the labels in the training, not the mean and standard deviation of the weights of the network.
No, it's the mean and standard deviation of the gradient of the weight for each layer. Okay.
You took all your images, you took them through the network, and from there you calculate the gradients and put out the mean and the STD.
Yes.
It's not the values of the weights themselves.
No.
Okay, just.
I also have a question.
Yes.
Does this happen with different hyperparameters? I mean, if you change the learning rate, or maybe if you change the data or the task itself? I mean, is this true now of neural networks in general, or?
So I will talk about it a bit later. Okay. It's a very good question. I will talk about it later.
And we also have a chat question. And Nadav is asking why the information of the label in the previous slide is always below 0.7.
Here?
No? Oh, maybe yes, I think.
So it's a binary. So actually, it's a binary task, and it's just the information with the information with the label. So it's a binary task, and like the labels were half 0, half 1. So it's a 0.7 information. Okay.
Another chat question: how exactly is the mutual information measured in the network?
It's a very good question. In this work, we just measured. We did the binning. We took, because we used the tangent hyperbolic tangent, so we can bin the values between -1 to 1. We can bin them, and then we just calculate. We discretize the probabilities, so we just calculate how many examples you have in each bin, and then calculate the probabilities and then the information. I will talk a bit again about different estimators and different works that try to do other things. Okay. More questions? Okay. Good. And the nice thing here is that the transition in the information plan for between the phases and this transition in the gradients occur at the same time. Okay, and you can also, if you shift this transition, you see that they shift together. Another thing that I wanted to show you is how overfitting looks in the information plan. So we trained a network with 80% of the data, and we trained a network with 5% of the data and 45% of the data. And you can see that that actually the first phase of the fitting looks pretty much the same. Okay. But the second phase of compression, actually this compression hurts you if you don't have enough examples. If you have small number of examples, this compression reduce reduces your performance. Okay. Another experiment that we did is to look on the optimality of the network. So the IB theorem gives us an optimal solution in some cases for the problem. So what we have done, we took the network output and we insert it to the IB equation, and we calculate the optimal solution for each one of the layers, and we also find the optimal beta by that. And then you can see, so this is again, it's the information plan, okay? So x-axis is the information with the input, and y is the information with the label. And the blue line is the optimal information bound from the IB, and the red points are the network output, the network layers, okay? And you can see that they are lying really close to the optimal bound, okay? The error bars are from different random initialization. Okay, now I want to talk a bit about the impact of this work. Actually, it was really cool because a lot of people try to take this work to many different directions. It has more than 700 stations, and like people, I learned a lot from some of these works. So I want to talk a bit about it. So there are 3 lines of work. One line of work is the information plan analysis, that people try to do the same analysis that we have done, but with different parameters, different estimators, different data sets, and just look on the information plan. How does the information plan look like? Okay. The second line of work is application that people try to use it for applications, and the third line of work is theory that people try to extend our theory. So the first line of work, as I said, is information plan analysis, and people try to put a lot of different estimators and different data sets and parameters and activation functions, and all these figures, for example, from different papers that try to do this and to look on the information plan. And if it's interesting you can look on this review paper that took some of these works and try to understand what is the bottom line of for each one of these works. And the bottom line is, I think, okay, personally, I think that the bottom line is that measuring information in neural networks is hard. Okay, people got different things, different observations with different networks and different estimators and different activation functions, and it's very hard to measure information in neural networks, and I will talk about it later. The second line of work is applications. So people took the IB objective and apply it to a neural network. Okay, so again, people did it for a lot of things. I really like the robustness work that people use the IB objective to make their networks more robust to adversarial examples and to overfitting and stuff like this. But people apply it also like to reinforcement learning and self-supervised and whatever. Okay. And And the third line of works is a theory that people extend the theory. And again, people took it to many directions. For example, people ask the question, where is the information? What is the important information quantity in the network? So we can think we looked on the information with the representation, but you can look also on the information with the parameters or the information with your data, and what is the relationship between all these quantities, okay? Okay. So now I want to talk about another work, okay? And in this work, we try to answer a very simple question. And the question is, where is the information in deep neural networks? Again, what are the important quantities and what are the important hyperparameters and how they related to each other? But what is the problem? The problem is that information is hard. It's hard to measure in neural networks. It's hard to quantify in neural networks. And as we saw, there are many different results. So, as I said, we want to look on the relationship between different quantities, information theoretic quantities, and compression and generalization, and how the hyperparameters affect on these quantities and these all these things. So we used information in infinite ensembles of infinitely wide neural networks. Now I will try to decompose this title and to explain exactly what are our assumptions that we need to make in order to measure and to explore these quantities. Okay? So let's start with infinite ensemble. What is infinite ensemble? So we are assuming that our parameters come from some distribution, some prior distribution, that we sample from some prior distribution, but now we take an ensemble over these initial parameters. Okay, so we're ensembling over the initial parameters, and we have an infinite ensembles that are coming from this prior distribution. The second thing is infinitely wide neural network. So we use the recent results from the Neural Tanget Kernels that says that it says that if you have infinitely wide neural networks, you have a tractable posterior distribution. Okay, it means that if Z is your output, so it's a Gaussian. It's a tractable. It's a Gaussian, and then using this tractable distribution, we can derive many information theoretic quantities, and we can play with them, and we can check the relationship between compression, generalization, and all these information theoretic quantities. Okay, so we use the infinite ensembles and we use the infinitely wide neural networks, and now we can calculate the information theoretic quantity. So, as I said, we heard from this paper, we know that our posterior distribution Z given X is a Gaussian that depends only on two kernels, the Neural Tanget Kernel and the NNGP kernel, and our data. So we can calculate, we don't need to train the network, we can calculate, give me the data and the network, I will calculate these two kernels, and now I can just put it in the equation, and I have a Gaussian. I know what is the distribution of Z given X. Okay? Good. Question? Okay. Now I have now after I have this tractable distribution, we derived many information theoretic quantities. The information with the labels and with the input and with the data, and between the data and the parameters, and also the feature information and many others. You can go to the paper and check all these quantities, and now we can play with them. So we have here, we played with 3 hyperparameters. One is the weight initial variance, right? We remember that we said that we sample our initial parameters from a Gaussian with some variance. Okay, so we can play with this variance. The second thing is the dataset size. What are the number of examples that of trained examples? And the third thing is the training time. For each number of steps, we have different representation and different results. Okay, so we played with them, and let's start with a Gaussian data.
Ravid, can I ask a question?
Yes.
So the MTK and the NNGP will depend on the architecture.
Right. Yes.
Not just on all these hyperparameters, but you have a very different kernel depending on the architecture. So
yeah. So maybe I didn't. Okay. So I said that if we fixed the network, the architecture of the network, and we played on only with this hyperparameter. There are many hyperparameters, but
what was the architecture? That's my question. Which architecture are you showing us now the results for?
Oh, okay. So first of all, okay, it's a good question. So this is a simple fully connected network. Okay. But for this case, we tried also convolutional network. But after it, I will talk about ResNet, about wide ResNet that we tried. But this is a fully connected network. Okay.
Yes, one more question. And the previous results were empirical results before the infinite were also for the fully connected network? The previous plots you showed of information.
Yes. But we can talk about it. But yeah, like a lot of other work try to do it for convolutional network and for a lot of other networks.
Thanks.
Okay. So as I said, we used a Gaussian data set. And the nice thing what is a Gaussian data set? So X and Y is a jointly Gaussian. So the nice thing in this problem is that the IV gives us an optimal solution. So this is the information plan. X-axis, the information with the input. Y-axis is the information with the label. And the blue line here is the optimal solution that, remember, it doesn't depend on any specific algorithm. And we played with the initial variance. Okay, so the different colors here are different variants. So we trained a network with some specific variant. We measured the information for this network. And as you can see here, that when you have high amount of information with your with the input, then the network is really close to the optimal bound. But when you force the network to reduce the information with the input, to compress, then in this regime, actually the networks are having a much worse representation, and they are far from the optimal representation, the optimal solution. Okay, so at least in this case, the networks are suboptimal. Okay, good. Now, the second thing that we looked is a double descent. So double descent is a phenomena that rediscovered last year, and say something simple, that if you're looking on your error as function of the model size, you will see that at the beginning, your error, okay, so the classical theory tells us that that at the beginning, the error goes down, okay? And then at some point, you will start to overfit and the error will go up. But what we really, we really see is that at some point, the error goes down again, okay? With the model size. When you increase your model size, the errors go down again, okay? And at least in the linear case, we understand it, and also for some nonlinear cases, but we don't understand it fully for the general case, in deep networks, the general deep networks. And what we have found is that now x-axis is okay. So this is for a CFAR. Okay, it's a CFAR data set. X-axis is the error, and y-axis is the information with the parameters. And remember that we can play with the amount of information that the network stores in its representation by changing the initial variance. So here, each point here is a network with different initial variance, okay, and the colors are different variances. And you can see here again that we see something similar to the double descent, that the error goes down, then goes up, but then it goes down again, okay? And it's very surprising because we have here infinite number of neurons, okay? It's an infinite wide neural network. So at least in this case, it's not the number of parameters or the number of neurons that matters, is the information with the parameters that affects your error, and you will see this double descent because you store more information with the parameters. Okay.
Can I ask about this one? Each point is just a simple initialization, and it varies. The information is varies.
So each point here is a different. Remember, it's an ensemble of networks. Okay, so each point here is an ensemble of networks over with a specific variance. Okay, and now you change the initial variance and measure the information for another ensemble of networks. Okay.
After training.
Yeah, this is after training.
Oh, okay.
Yeah, sorry, it's after training. Yeah. Okay.
Wait, I'm confused. These are the infinite networks, so you're not really. You don't actually train them. You use the kernel.
Right. Yeah, but the kernel your kernels depend on the time.
So the every data point here is the result of training just the kernel classifier, not training a neural network.
No, so it's a long, let's say, discussion. What does it mean, neural tangent kernels, right? But what is the connection between neural tangent kernels and network to real network? And
I don't want to get into that discussion, but it's just a question. When it says 4 times 10 to the minus 1 error,
yeah,
how is that number calculated?
So it's the performance. It's the performance. You have a prediction from the neural tangent kernels, from the neural tangent networks, right? You have a prediction, okay? You have prediction, and then you calculate the error based on these predictions.
Okay.
So Ovid, it's the kernel or a neural network? I think that's what he is asking.
it's a neural net. It's a neural network that's based on. It's an infinitely wide network.
No, but you can't really program an infinite network, right?
What do you mean?
Explicitly so. So you must be using the kernel trick in order to train the kernel.
Yeah, it's the NTK.
Yeah.
It's the NTK. It's the NTK. It's not. It's the approximation of infinitely wide networks. It's not a real network in the sense that you cannot train it, right? You just can. You need to plug in in the kernels and then calculate for each T. But it looks that, at least from several papers, that it looks that it's a good approximation to real networks.
Yes, you're probably aware that Ohad has papers that argue the opposite, but we can discuss that later.
Yeah. No. Okay. Yeah. It's a good question. Okay. Let's say something else. It's a good question. I understand it's a good question how real networks related to infinitely wide network and to the kernels and to the NTK. But if neural network, if neural tangent kernel is a good approximation to neural networks, then you can look on the information. Okay, but I agree that it's not a specific network. Yeah, more questions? Okay. The third thing that we found is now we have the information with x-axis the information with the input, and y-axis is the error, and here the different colors is the number of examples. Okay, and now we can see here. So, for example, at this point, okay, if you don't have if you have small number of examples, when you force your network to store more information, it starts to overfit. Okay, it starts to overfit really quickly. But when you increase the number of examples, then you see that the network can store more information, and the point that it starts to overfit goes to the right. Okay, and you see here that you increase the number of examples till here that the network overfits only when you can store a lot of when it stores a lot of information. Okay, so this is actually, it's really cool that let's say empirical evidence to all the to generalization gap bound, that when you have small number of examples, you will overfit if your information is high, if information with the input is high. But when you have a lot of examples, you will not overfit if you increase the information with the input. Okay. I don't have a lot of time, but I will talk about the third thing briefly. So the dual information bottleneck, okay? And in this work, we tried to suggest a new framework, and we tried to address some of the limitations of the information bottleneck. Okay, so one limitation is that let's remember now that we have X and we have the labels Y and we have our representation T. Okay, but the information bottleneck tries to maximize the information with our labels, the information of our representation or model with the labels, and we ignore the predicted labels. We are assuming that it's an optimal base decoder, and we ignore this random variable, the predicted labels. And another limitation is that the information bottleneck ignore the structure of the data. Okay, if we have structure in our data, we want to take it into account. So, for example, we have some parametric model. We have in this example exponential family. Okay, so we have some that our data comes from this distribution. We have some constraints on the expectations, and now why to use this kind of model? So it's apparently it's the distribution that we need minimum assumptions given the constraints, or maximum entropy given some constraints. It says a natural sufficient statistics, and we can use these sufficient statistics. We can calculate everything based on these sufficient statistics, and we can get reduction in the computational complexity if we use these sufficient statistics. Okay, and we have it in many problems, many physical problems. If you have some Hamiltonian and stuff like that. So let's see how the IB, the original IB, tries to deal with this. So the IB function, distortion function, is this: is the DKL between our data, y given h is our data, and y given t is our model. Okay, and we want to minimize this functional. So we want to minimize again these two terms, the information with the input. We want to compress, and we want to keep the relevant information about the label. Now, in the original paper, they showed that you can get an optimal solution by these self-consistent equations, okay, for the encoder and for the decoder. But what is the problem? That if we assume that our data has is from exponential family, then the IB does not preserve this parametric from. Okay, and we have a decoder that is this decoder that doesn't preserve the parametric form of the exponential family. So let's try something different. Okay, we suggested to use the dual information bottleneck. Why dual? Because here we use the dual distortion function, and we switch the order in the DKL. Okay, now we have DKL between y given t and our labels y given x. Okay, and now we want to minimize this functional, and apparently that the solutions are also self-consistent equations, but now we have a different equation, and now you can see here that at 3 we have here a geometrical mean in the solution, and we have here in the decoder we have exactly what we want, that the sum is inside the exponent. But look that here that in this normalization term it depends on t. So it's apparently that that in the dual IB we are focusing not on the maximize the information with the labels, but maximize the information with the predictions. Okay, so the third equation in the last slide says that we are maximizing information with the prediction, and we are focusing on this information. And now we're not assuming an optimal base decoder as we have done in the original IB. And now let's look how does it look on the information in the exponential, if we assume that our data is from exponential family. And now the optimal solutions are again from exponential family. So the optimal solutions for the duallB, the optimal sub solutions are from exponential family, and we have we know what are these solutions by the duallB. Okay. Good. Now let's try. I don't have a lot of time, so I will do it quickly. Let's try to apply.
Just a quick question. So for the case of an exponential family, you get what you want, but like if I have some other kind of parametric family, or maybe more specific one, would the same thing work? And also, why can't you simply try to minimize, instead of this approach, just try to minimize the functional under the constraint that you want this particular parametric form? I mean, is it intractable, or is there some other problem?
I don't think you can, like, to do it. I don't think you can do it. You don't. I don't think you have a closed form for if you minimize it with these constraints.
Mm-hmm. Okay, and if you want a parametric family which is not an exponential family, or something more specific,
what like more specific, like that exponential family, like Gaussian or something like that, like more specific inside from exponential family?
I'm just trying to understand how generic the solution here, how generic the solution is. Like your motivation was that if we have an exponential family, then the standard information bottleneck doesn't give us what we want, and this dual formulation does. So I'm asking if it's generic, or it's really a solution for exponential family.
So so for exponential, I think it's heavily related on this. That the solution is this. Okay, the solution, the self-constant equations are this, and these are like it's is a form of exponential family, this geometrical mean. Okay.
Okay.
The last thing that I wanted to show you is that we apply to deep neural network. Okay, and as you already know, that information in neural network is hard. So use a approach that says something very simple. Let's use a variational approximation of the IB, and now let's parameterize the IB using a neural network, and let's maximize the variational bound of the IB. Okay, and the nice thing in this bound that we can take all these terms to be neural network, to feed them with neural network, and then to train it end-to-end with SDD, and everything is okay. So this is called the deep variational IB. And we took a similar approach. So we derived a variational bound on the duallB, okay? And now we can use the same thing and to fit all these terms with neural network. The only problem is this one, okay? Y given X. So our problem in the duallB that this cannot be a zero, okay? Because it's inside this term, so it cannot be zero, and we must assume some noisy labels, okay? That P of Y given X is not zero, but it has some noise. I will talk about it later a bit, but this is the bound that we try to maximize using neural networks. So here we compare the two models, the variational duallB and the variational IB. So this is the information plane. X-axis, the information with the input. Y-axis is the information with the labels. And the different colors here are different values of log beta. So remember, we train a network with a specific value of beta, okay? And as you can see here, at least in the variational case, the duallB is much more efficient and has a compressed representation compared to the variational IB. And the last thing that I wanted to talk is the noise model. So as you can see in the distortion function of the duallB, P of y given x cannot be zero. So we must assume some noise model on our label. Okay, and there are several works that try to use noisy labels. But in this case, we tried several models. So you can take a Gaussian noise to inject a Gaussian noise into your labels. You can take the prediction of another trained model as your noisy labels, etc. So here we compare different noise models. So this is again the information plan, information with the input versus the information with the labels. And we can see here that, so each color here is a different noise model. And we can see here that the bottom line is that the noise model is actually really matters to the performance, the representation, and you need to take care what is your noise model in this frame. Okay, so I'm almost out of time. I want to summarize. We talked about information in deep neural network. We saw these two phases, fitting versus compression, and we talk about information in infinitely wide neural network. We derived many information theoretic quantities and look on generalization versus compression in this framework. And at the end, we talk about the dual information bottleneck that preserves the structure of the data if you have an exponential family distribution, and we saw how we can apply to deep neural networks. That's it. Questions? Okay, so
No
I want
questions?
to thank to my supervisor, Tali Tishby, and that's it.
And I want to thank Ravid for this amazing talk. And we will meet again after Passover in 3 more weeks. So see you all.
Glad we will meet in person, right?
Hopefully, yeah. Hopefully we can come and meet in person in the university. Yeah.
Hopefully, yes.
Yes.
Bye-bye.
Okay.
So just Ravid's committee, I hope they know who they are. We'll meet in a different meeting in a few minutes. So we should send some link to another Zoom. Okay, thank you.
And for the students who are taking the seminar for credits, please stay after this talk. תישארו הסטודנטים שלוקחים את זה לקרדיט. אנחנו נדבר עכשיו בלינק הזה.
ביי, תודה.
ביי, תודה רביד.
תודה.